Dear students, welcome to the first lecture of Physics for Class 11. In today's lecture, we will study chapter number 1 titled Physical World. Humans have always been curious about the world around them. The night sky with its bright celestial objects has fascinated humans since time immemorial. The regular repetitions of day and night, the annual cycle of seasons, the eclipse, the tides, the volcanoes, the rainbow have always been a source of wonder. The world has an astonishing variety of materials and a bewildering diversity of life and behavior. The inquiring and imaginative human mind has responded to the wonders and awe of nature in different ways. One kind of response from the earliest time has been to observe the physical environment carefully, look for any meaningful patterns and relations in natural phenomena, and build and use new tools to interact with nature. This human endeavor led in course of time to modern science and technology. In this chapter, we will study section 1.1 to 1.5 covering what is physics, scope and excitement of physics, physics, technology and society, fundamental forces in nature, and finally, nature of physical laws. What is physics? The word physics comes from a Greek word meaning nature. Physics is a scientific study. Please underline scientific study of basic laws of nature and their manifestation in different natural phenomena. In physics, we attempt to explain diverse physical phenomena in terms of a few concepts and laws. For example, laws of gravitation and laws of electromagnetism. We will study about laws of gravitation in detail in subsequent chapter in class 11, that is this class itself, and laws of electromagnetism in class 12. As we have said earlier, physics is a scientific study. So, what is science? Science is an attempt to understand physical phenomena in detail and in depth. And the methods adopted to understand science are scientific methods. The scientific methods are systematic observations, controlled experiments, qualitative and quantitative reasoning, mathematical modeling, predictions, and verification or falsification of theories. When we say verification, that means we have to prove certain concepts, certain laws, certain theories. And falsification is opposite of verification. That is, falsification means we have to disprove certain assumptions, certain theories, and cross-verify and present the correct thing. Scientific methods are extremely extensively used in physics to study explain and prove the concepts, theories, and experiments. Physics is a basic discipline in the category of natural sciences, which includes other disciplines like chemistry and biology. Certain parts of chemistry and biology are also studied in physics and vice versa. Scope and excitement of physics. We can get some idea of scope of physics by looking at its various subdisciplines. The two domains of interest in physics are macroscopic and microscopic. Macroscopic. The macroscopic domain includes study of phenomena, finite size objects at laboratory, terrestrial, and astronomical scales. Terrestrial refers to anything that comes from the planet Earth, like land, rocks, elements, oceans, etc. etc. And astronomical scale refers to the study of universe with unbelievable sizes and distances, like stars, planets, moons, distances between them, the size of planet, size of sun, size of earth, diameter of earth, the distances between the time measurements for revolution, earth's revolving and earth's cycle, etc. are studied in terms of astronomical scales. Microscopic domain deals with constitution and structure of matter at minute scales of atom. As you know, atom is the smallest part of an element. So, in microscopic studies, we refer or we study in subatomic scales, that is, parts of an atom like nuclei, electrons, protons, and large number of other particles, that is on a very minute scale, that is subatomic scale. The classical physics deals mainly with macroscopic phenomena, and it includes subjects like mechanics, electrodynamics, optics, and thermodynamics. In mechanics, we study Newton's laws of motion, laws of gravitation, and general system of particles. The subject electrodynamics deals with electric and magnetic phenomena associated with charged and magnetic bodies. That also includes study of charges, includes charges, stationary static charges, charges in movement, and subsequently we conclude or we continue our studies on radio waves. These are all parts of electrodynamics. Optics. Optics deals with study of light, rainbow, scattering, mirage, optical instrument, lenses, microscope, telescope, etc. In thermodynamics, we study systems in macroscopic equilibrium, which deals with changes in internal energy due to change in temperature or entropy, etc. of the system through the external work. That is, when external work is done, heat is produced, and that study of internal energy is thermodynamics. The efficiency of heat engines and refrigerators, the direction of physical or chemical processes are studied in thermodynamics. Thus, the scope of physics is very vast and it covers a wide range of lengths, that is 10 to the power of minus 14 meters to 10 to the power of plus 26 meter of lengths, and in for masses the range is approximately 10 to the power of minus 30 kg to 10 to the power of 55 kg, and in time measurements the ranges are 10 to the power of minus 22 seconds, that is very small times, to 10 to the power of 18 seconds. And other physical quantities like force and energy is also included in the scope of physics. Physics, technology, and society. The connection between physics, technology, and society can be established by studying the applications and benefits of technology to improve the quality of life in a society. For example, thermodynamics deals with theory of heat engines, which in turn brought industrial revolution in England during 18th century. This revolution greatly impacted the course of human civilization. The discovery of electromagnetism in 19th century led to the development of new technology of wireless and radio communication. The benefits of applied physics are being reaped by all sections of the society. The nuclear reactor used for generating electricity is due to discovery of fission reaction of uranium. Hence, the nuclear energy can be used for peaceful purposes or as well as destructive purposes. The application and development of microchips and chips and optical fiber is being used extensively in computer, radio communication, TV, video, long distance communication, satellite communications, and all forms of telecommunication system, which in turn has transformed the world into a global village. Similarly, the theory and application of photoelectric effect is used to generate solar energy. Solar energy is a new form of electrical energy which has got wide range of applications. To sum up, the names of some great physicists and their contribution are listed in table 1.1 in the next, and the link between technology and physics is tabulated in subsequent table. Physicists and their contribution. Please see the following table. In the first column, name of physicists are given. In the second column, contribution and discovery, their contributions is given in the second column, and the country of their origin is given in the column number 3. For example, Archimedes discovered buoyancy and lever. So he was from Greece. Galileo Galilei gave the law of inertia and he belonged to Italy. Christian Huygens gave the wave theory of light. Isaac Newton gave the laws of gravitation, motion and reflecting telescope. Michael Faraday gave the laws of electromagnetic induction, which was applied in electricity generation. And Michael Faraday belonged to UK. James Clerk Maxwell discovered the electromagnetic theory of light and correlation between light and electromagnetic wave theory. Hertz. Heinrich Rudolf Hertz, a German scientist, gave electromagnetic generation. Sir Jagdish Chandra Bose, his contribution is ultra short radio waves. So he is an Indian scientist. Roentgen gave X-rays, Thomson electron, Marie Curie radium, polonium and radioactivity, and Albert Einstein, a very important and very great scientist, gave the photoelectric effect and theory of relativity. Hence, in this table 1.1b, which is a continuation of previous table, also lists a number of physicists and their contribution as well as country of origin. Please go through this list and remember their country of origin and contribution. Important among them are also given here. Like India, we have M.N. Saha who gave thermal ionization and S.N. Bose gave quantum statics India and S. Chandrasekhar gave Chandrasekhar limit structure and evolution of stars. Like that so many scientists are there. C.V. Raman, like example, C.V. Raman gave scattering of light. Please note down all important names of physicists, their contribution and country of origin. Table 1.2 gives the link between technology and physics. So, important technologies are given in column number 1 and the scientific principle used is given in column number 2. For example, steam engine works on the principle of laws of thermodynamics. Nuclear reactor works on the principle of controlled nuclear fission. Radio and TV works on electromagnetic waves. Computers work on the principles of digital logic. Lasers work on emission of radiation. And ultra high magnetic field works on the principle of superconductivity. Rocket propulsion works on the principle of Newton's law of motion. Electric generator a generator works on Faraday's law of electromagnetic induction. Hydroelectric power works on the principle of conversion of potential energy into electrical energy. Aeroplane works on Bernoulli's principle of fluid mechanics. Particle accelerators work on the principle of motion of charged particles. Sonar, reflection of ultrasonic waves. Optical fibers, total internal reflection of light. Non-reflecting coatings, thin film optical interference. Electron microscope, wave nature of electrons. Photocell works on photoelectric effect. Fusion test reactor, magnetic confinement of plasma. Giant meter wave radio telescope, GMRT. I read once again, giant Meter wave radio telescope GMRT works on principle of detection of cosmic radio waves. And Bose-Einstein condensate works on tapping and cooling of atoms by laser beams and magnetic fields. Having studied about what is physics, scope and excitement of physics, and physics, technology and society, now we will take a fresh section, fundamental forces in nature. In everyday experience, we encounter several kinds of forces like gravitational force, frictional force, the force of buoyancy, the viscous force, contact force between bodies, the force due to the surface tension of a liquid, and so on. In last part of 20th century, scientists have found different forces occurring in different contexts and from a very small number of fundamental forces in nature. There are four fundamental forces in nature which may be described as: number one, gravitational force. The gravitational force is the force of mutual attraction. Please note, mutual attraction between two bodies or two objects by virtue of their masses. So, gravitational forces is mainly due to mass between two objects and it is only attraction in nature. It is a universal force. Every object experiences this force due to every other object in the universe. It governs the motion of celestial bodies, formation and evolution of stars, galaxies, galactic clusters due to gravitational attraction. The next force, that is serial number 2, is weak nuclear force. The weak nuclear force appears only in certain nuclear processes such as beta decay of a nucleus. In beta decay, the nucleus emits an electron and an uncharged particle called neutrino. More details of weak nuclear forces will be studied in class 12. In serial number 3, we have electromagnetic force. Electromagnetic force is the force between charged particles. Please note charged particles. In the simpler case, when charges are at rest, the force is given by Coulomb's law. This force can be attractive between two unlike charges and it can also be repulsive between two like charges. That is, like charges repel and unlike charges attract. Charges in motion produce magnetic effects and a magnetic field gives rise to a force on a moving charge. About electromagnetic force, we will study in detail in class 12. At serial number 4, we have strong nuclear force. The strong nuclear force binds protons and neutrons in nucleus. It is evident that Without some attractive force, a nucleus will be unstable due to electric repulsion between its protons. We know that in the nucleus there are protons and neutrons. Protons are positively charged, hence in normal case this should have been a repulsive force. But because of strong nuclear force, there is a binding between protons. The attractive force cannot be gravitational force since force of gravity is negligible compared to the electric force. Unification of forces. In physics, we attempt to explain diverse physical phenomena in terms of few concepts and laws. The effort is to see the physical world as manifestation of some universal laws in different domains and conditions. For example, the same law of gravitation, which is given by Newton, describes the fall of an apple to the ground, the motion of moon around the earth, and the motion of planets around the sun. Similarly, in case of electromagnetism, that is Maxwell's equations, govern all electric and magnetic phenomena. The attempts to unify fundamental forces of nature reflect this same quest for unification. So a related effort is to derive properties of a bigger or more complex system from the properties and interaction of its constituents and similar parts. Unification. The basic laws of gravitation explains the fall of an apple, earth rotation, motion of moon and planets, etc. Reductionism. In this approach, bigger systems are analyzed using simpler interactions and parts. That is, bigger systems are split into smaller ones and the phenomena is studied. For example, molecular theory and thermodynamics. Table 1.4a in the next slide gives the relative strength, range, operational characteristics of the fundamental forces of nature. As we have seen earlier, there are four fundamental forces of nature, that is gravitational force, weak nuclear force, electromagnetic force, and strong nuclear force. Their relative strengths are given in terms of numbers. That is, the gravitational force is weakest of all and its relative strength is 10 to the power of minus 339. That is, if strong nuclear force is 1, then gravitational force is 10 to the power of minus 39 and weak nuclear force is 10 to the power of minus 13 and electromagnetic force is 10 to the power of minus 2. The range of this force, the gravitational, is applicable over an infinite range, a very large range. It can be operational and it operates among all objects. And weak nuclear forces is very short and subnuclear size approximately is equal to 10 to the power of minus 16 meters. It can it is functional only at a very short distance. It operates between electron and neutrino. And electromagnetic force is infinite and it is between charged particles. Whereas The strong nuclear force is short. It is approximately equal to 10 to the power of minus 15 meters. It operates between nucleons, heavier elementary and particle. To sum up, we'll study about gravitational forces in class 11, and we'll study weak nuclear force, electromagnetic force, and strong nuclear force in class 12. Unification of different forces and domains in nature. These are the studied and shown by different scientists and physicists. Isaac Newton in the year 1687 unified laws of celestial and terrestrial mechanics. That is celestial and terrestrial. Celestial means universal, that is sun, moon and celestial bodies, and terrestrial is anything on the land. Harris Christian Oersted and Michael Faraday in the year 1820 to 1830 and 1830 unified electric and magnetic domains and developed theories of electromagnetism. James Maxwell in 1873 gave the theory of electromagnetic theory of light. Abdul Salam, Sheldon Glashow, and Steven Weinberg in 1979 showed that weak nuclear force and electromagnetic force could be viewed as a different aspects of a single electric weak force. Claro Rubia, Simon van der Meer in the year 1984 verified experimentally the predictions of theory of weak forces. Nature of physical laws and conserved quantities of nature. In any physical phenomenon governed by different forces, several quantities may change with time. A remarkable fact is that some special physical quantities, however, remain constant in time. They are conserved quantities. That means the conserved quantities do not change and remain constant in time. For motion under external conservative force, the total mechanical energy, that is the sum of kinetic energy and potential energy, is constant. The familiar example is free fall of object under gravity. Both kinetic energy of the object and its potential energy change with time, but the same sum remains same. That is, the kinetic energy may be zero at certain point of time. So, but the total energy, that is potential energy plus kinetic energy, will be the same, fixed. If the object is released from rest, the initial potential energy is completely converted into kinetic energy of the object just before it hits the ground. That means when the body is moving, there is a kinetic energy, and body is at rest, it is a potential energy. So when body is at rest, potential energy is there, but kinetic energy is zero. When body is moving, kinetic energy will be there and potential energy may be zero. When all forms of energy, example heat, mechanical energy, electrical energy, etc., are counted, it turns out that energy is conserved. The general laws of conservation of energy is true for all forces and for any kind of transformation between different forms of energy. Until the advent of Einstein's theory of relativity, the law of conservation of mass was regarded as another basic conservation law of nature, since matter was thought to be indestructible. It was and still is an important principle used, for example, in analysis of chemical reactions. As we have seen In the previous slide, conserved physical quantities are those quantities that remain unchanged in a process. These are some general conservation laws in nature, that is conservation of mass, energy, linear momentum and angular momentum, charge, etc. There are some conservation laws that are true for one fundamental force but not for the others. A chemical reaction is basically a rearrangement of atoms among different molecules. If the total binding energy of the reacting molecules is less than the total binding energy of the product molecules, the difference appears as heat and reaction is exothermic. Exothermic means along with the changes due to chemical reaction, there is heat is also generated or heat is released. According to Einstein theory, the energy E is given by the relation E is equal to mc square, where c is the speed of light in vacuum. In a nuclear process, mass gets converted into energy. Please see this equation of relativity. E is equal to mc square. On the left side, E is the energy, and the right hand side it is mass. So energy is getting converted into mass or vice versa. This is the energy which is released in a nuclear power generation and nuclear explosions. Please note that energy is a scalar quantity, but all conserved quantities are not necessarily scalar. Linear momentum and the total angular momentum are both vectors of an isolated system. They are also conserved quantities. So, energy can be a scalar quantity and all conserved quantities not necessarily be scalars. The laws of momentum can also be derived from Newton's law of motion in mechanics, but their validity goes beyond mechanics. They are basic conservation laws of nature in all domains, even in those where Newton's laws may not be valid. Besides their great simplicity and generality, the conservation laws of nature are very useful in practice. It often happens that we cannot solve all the full dynamics of a complex problem involving different particles and forces. The conservation laws can still provide useful results. Symmetries of space and time. Laws of conservation have a deep connection with symmetries of nature. Symmetries of space and time and other types of symmetries play a central role in modern theories of fundamental forces in nature. The laws of nature are same everywhere in the universe. The symmetry of laws of nature with respect to translation in space gives rise to conservation of linear momentum. In the same way, isotropy of space No intrinsically preferred direction in space underlies the law of conservation of angular momentum. The conservation laws of charge and other attributes of elementary particles can also be related to certain abstract symmetries. Symmetries of space and time and other abstract symmetries play a central role in modern theories of fundamental forces in nature. With this, we complete our discussions on chapter number 1, that is physical world. Let us conclude by summarizing what we have learned in this chapter. Point number 1. Physics deals with the study of basic laws of nature and their manifestation in different phenomena. The basic laws of physics are universal and apply in widely different contexts and conditions. That is, the physics deals with basic laws of nature, and these laws are universal and are used very widely in different contexts and conditions. Point number 2. The scope of physics is wide, covering a tremendous range of magnitude and physical quantities. Point number 3 is physics and technology are related to one another. Sometimes technology gives rise to new physics, at other times physics generates new technology. Both have direct impact on society. Point number 4. There are four fundamental forces in nature that govern the diverse phenomena of macroscopic and microscopic world. These are gravitational force, electromagnetic force, strong nuclear force, and weak nuclear force. Unification or combination of different forces or domains in nature is a basic quest in physics. The physical quantities that remain unchanged in a process are called conserved quantities. For example, laws of conservation of mass, energy, linear momentum, angular momentum, charge, parity, etc. These remain unchanged and are conserved quantities. Some conservation laws are true for one fundamental force but not for the other. Conservation laws have a deep connection with symmetries of nature. Symmetries of space, time and space, and other types of symmetries play a central role in modern theory of fundamental forces in nature.